Let's look at an example where we deal with an unsteady flow and the conservation of mass. Let's say we have a tank with some volume V, and it's filled with some gas at density rho, and shooting out of this tank at time 0. So at time 0 we have the tank and it's full, and then we open up the valve, and at time t equals 0, and out comes the gas at some velocity, which I'll call v1, and some density, which I'll call rho1, and it may or may not be the same as the density inside the tank, depending on the complexity of the flow. We'll say that the area here, we'll call it A1, and we'll assume that we have uniform velocity, and we'll assume we have uniform density, both inside the tank, density rho, and in the jet leaving, density rho1, which again may or may not be equal to each other. If we write out the conservation of mass, which we developed from the Reynolds transport theorem, we see d dt of the integral over the control volume of rho dv plus the integral of the control surface of rho v dotted with n hat dA has to equal 0. And this time we don't get to cross off the first term because we are considering unsteady flow. There was a change in density over time within this volume here, and so we can't just ignore that and cross it all off. Because the density is constant throughout the volume, though, this integral over the control volume just returns the volume, and so we end up with d dt of the quantity rho times the volume plus the integral over the control surface of the mass leaving the control surface equals 0. Well, looking at the control surface, if we assume that the velocity is constant across the surface and the density is constant across the surface, then this is all going to just reduce to rho 1 v1 a1 equals 0, where we note that the direction of the velocity and the direction of the normal pointing vector are the same, and therefore v dotted with n gives us a positive number. So because the volume is not changing with time, we can take that outside of the derivative, and then we can solve for the change in density over time, d rho dt, and that's just going to be equal to minus rho 1 v1 a over the volume of the container. If you remember correctly, this is just the mass flow rate, and so the change in density is just equal to the mass flow rate out of the system divided by the volume, and it's negative because the density will be going down as mass is leaving the system.